In this video or videos, we'll see how far we get and how many we have to make. We'll review Stokes' theorem and go over as many examples as we can in a reasonable amount of time to illustrate the use of Stokes' theorem. So let's continue by reviewing what Stokes' theorem says. Recall there are several ingredients at play here. The first is some surface S, and we assume that the surface S has an orientation. And in this picture, I have indicated that orientation by drawing several tangent vectors pointing out normal to the surface S. The second ingredient is a curve, a closed curve C, which is the boundary of S. That's this thing down here. And we impose the condition that C has an orientation as well, that is a direction of travel. And what is required of these two orientations, the orientation of S and the orientation of C, is that they are compatible in the right-hand rule sense. And what I mean by that is, as one would curl their fingers around the direction of travel around C, that would be in the counterclockwise direction, your thumb should point in the direction of the orientation of S. So you can imagine if you curl your fingers in this direction going around C, your thumb will point in the upward direction, which I have indicated here, which is the direction of the orientation of S. So we say that these two orientations are compatible. If they are compatible, then Stokes' theorem applies, which is the equality between two different kinds of integrals. This one I've written here on the left is the surface integral, which is the flux of the curl of f on the surface S. And this one on the right is the line integral of f around the closed curve C. Stokes' theorem says that these two integrals are the same. That's it. So in our examples, which we'll look at in just a minute, we will either calculate, or we'll find, I should say, we'll find the left-hand side by calculating the right-hand side, or we'll find the right-hand side by calculating the left-hand side. Sometimes one side is easier to do than another side. That's a good reason to use Stokes' theorem. So without any more delay, here's our first example. So I need a vector field, which I have here. I have a vector field f, which is given by xyz equals negative y squared, comma x, comma z squared. And I have a curve C, which is the intersection of two surfaces. And this is the example that we left off on at the end of class on Wednesday. So we drew a picture on Wednesday, the intersection of the two surfaces, one of which is a plane, and the other of which is a cylinder. We drew a picture of this in class. Here's the cylinder, x squared plus y squared equals 1. And then we intersect that with the plane y plus z equals 2, which gives us this curve C, which I've drawn in red here. I haven't drawn the plane, but you can imagine the plane sort of cuts through like this and then slices or intersects the cylinder. So our question for this problem is to find the line integral of f around this closed curve C, this thing down here. Now, there are two ways we could go about this. I'm going to go ahead and do them both ways. So the first method is to appeal directly to the definition of the line integral of f, and to go back and use those methods which we learned earlier in chapter 16 to do this directly. That is, do this by parametrizing the curve C. The second method would be to use Stokes' theorem. So I can write PAR for parametrizing, or ST hoc ES for Stokes. Those are two different methods we can use to find this. We're going to do both of them for two reasons. One, so we can just get some more practice, and two, so that we can actually check our answer. So let's go ahead and first do the first method, which is the method of parametrizing the curve C and calculating this integral directly. So here's method 1, direct calculation. Well, if we calculate directly, we have to begin by finding a parameterization for the curve C. So remember the curve C looks like this sort of tilted ellipse. So how do we parameterize that curve C? Well, we know that this curve C at least projects down onto the xy plane as a circle. And as a circle in the xy plane, it has equation x squared plus y squared equals 1. And that's how we know this. Since x squared plus y squared is equal to 1, we know in particular that y has to be between negative 1 and 1, and therefore y must be equal to sine theta, and hence x is equal to cos theta. This is just a complicated way of saying that we can always parameterize the unit circle by writing y equals sine theta and x equals cos theta. And we've done this many times before, so this should not be mysterious at all right now. Okay, so then what do we need? We need to parameterize the curve C, which is up here floating in space. We have the function for x that we'll use in our parameterization. Whoops. We have the function for y that we'll use in our parameterization. So the only question remaining is, what is z? Right? Well, we can solve for z because remember this thing lies on the plane. And on the plane, z is equal to 2 minus y. And if y is equal to 2 minus sine theta, then we have solved for z. Z is equal to 2 minus sine theta. Great. So we have a parameterization of c. Let's write it down. Here's our x cosine theta. Here's our y sine theta. Here's our z 2 minus sine theta. Now, what are we going to need to fill in or to calculate that integral over c of f dot dr? Remember, I'll let you recall briefly what the parameterization looks like. We want to calculate this thing over here. We parameterize by rewriting it as this thing over here. And so here are the ingredients we need. We need the parameterization. That's this thing right here. We need to evaluate f at the parameterization. That's this thing right here. And we need to take the dot product of that with the derivative of the parameterization. That's this thing right here. So we need this thing, and we need this thing. So let's calculate them. So here I have r prime theta. It's negative sine theta, comma cos theta, comma negative cos theta. And also I've taken f and evaluated it at r theta. That's this, and so that gives me negative sine squared theta cos theta and 2 minus sine theta squared. Remember, for this one, I needed the original definition of the vector field f, which was what? Negative y squared comma x comma z squared. So I just evaluated each of those at their corresponding component functions up here. Great. Now we're ready to calculate our line integral of f, and we replace it with its parameterization. That's this thing over here. I didn't write this above, but the limits on our parameterization are from 0 to 2 pi. That's what we get to go all the way around the ellipse. And now we replace f of r theta with this vector expression up here, which we obtained above. And we replace r prime theta with this vector expression, which we also obtained above. And now we only need to take the dot product of all of this stuff before we actually calculate the integral. We take the dot product, so